Hi there, I'm Dr. Ben Raymer, President ad interim of UTMB in Galveston. Our institution is honored and thrilled to sponsor the Thought Leaders Lecture Series. As an academic medical center that provides comprehensive, high-quality, and accessible care across the entire Bay Area and down into Galveston, we are proud to partner with Space Center Houston to bring you these stimulating talks featuring some of the best, brightest minds of our time, sharing their views on a wide variety of complex scientific topics. While the COVID-19 pandemic continues to unfold and dramatically change our daily routines, teams of individuals across our institution are working to counter the virus on all fronts. We're caring for those impacted by the disease, testing those who are sick or who have been exposed, and working hard in our laboratories to better understand how this virulent threat behaves. We hope that these engaging and educational lectures provide you a needed respite during these trying times and serves as a reminder to you that humans have the capacity to do great and brilliant things, even in the face of adversity. Thank you and be well.
Hello, I'm William T. Harris, President and CEO of Space Center Houston. We are a nonprofit and dynamic science and space exploration learning center. We're also the official visitor center of NASA Johnson Space Center. We share the story of human spaceflight with more than 1.25 million visitors annually from around the world. Thank you for joining Space Center Houston's Thought Leader Series, Human Robotic Interaction, presented by the University of Texas Medical Branch. Our Thought Leader Series brings you space and science experts from around the world to provide insights and perspectives on space exploration. This year, we're celebrating 20 years of continuous human habitation on the International Space Station. Our Thought Leaders topics honor the ISS and its significant achievements and benefits to humanity and space exploration. As we navigate this unique period, Space Center Houston is committed to supporting our community with authentic science learning experiences. We also look forward to reopening on July 1st for guests to enjoy our science and space exploration artifacts. We'll offer exclusive member days June 28th to the 30th. We want you to be inspired through our authentic science learning experiences and a sanitized and safe environment. With new exhibits, spacious outdoor experiences, and additional health and safety measures at the forefront of our daily operations, we will reopen with limited capacity to provide a safe environment. Guests will save time in line with advanced timed admission tickets to enable a staggered guest entry. We anticipate reopening with one of the most popular experiences, the NASA Tram Tour, which takes guests behind the scenes at NASA Johnson Space Center. And no more waiting in lines. Through Space Center Houston's free app, you can select and reserve seats at a designated time on the tram tour that you wish to board. Several new protocols are in place to ensure a safe and welcoming experience at Space Center Houston. A new Apollo 13 Failure is Not an Option exhibit will open that describes the mission as it unfolded with unique artifacts from our permanent collection and new additions that are rarely on display. You can also experience our new permanent outdoor exhibit, a flown SpaceX Falcon 9 rocket. It's the only Falcon 9 on display outside of SpaceX's headquarters, and it's the same type of rocket used in the Demo 2 mission. This was the first commercial crew program launch with astronauts at the International Space Station and marked the first time since 2011 that astronauts have launched from American soil. Plan your journey with us today. Go to spacecenter.org/open to review our Know Before You Go guide for tips on planning your visit. You can purchase time tickets today at spacecenter.org. While our facility is not open to the public, Space Center Houston is offering robust virtual learning experiences. We've held several successful virtual campouts, and we have one coming up on June 19th. You can gaze at the stars with us, and we'll make science come to life in your own backyard. Take a virtual tour of the museum, download the Space Center Houston free app for augmented reality, videos, and audio stories about the past, present, and future of human space exploration. The app is available for Apple and Android devices. You can also learn about activities for students and families that you can do together through our Try at Home vlog series. You can follow us again on our website, spacecenter.org, where you can connect on all of our social media platforms for the latest engaging content. We are very excited about opening on July 1st and welcoming you back to Space Center Houston. Until then, please enjoy exploring space and Space Center Houston through our digital resources page. To help bring this content to you, we ask that you consider becoming a member or making a donation to help bolster and expand our digital delivery of education resources for the community. You can again do that through our website at spacecenter.org. And now on with our panel, Human-Robotic Interaction, presented by UTMB. We are very excited to learn about NASA's innovative rovers, dynamic exoskeletons, and autonomous Robonauts. In today's presentation, our experts will take us through the innovation happening now in robotics and give us a look into the future of space. We're going to hear from NASA robotics experts Dr. Laura Lucier, Dr. Kimberly Hammakin, and Maria Bulat. Now I'd like to introduce our panelists. Laura Lucier, PhD, currently serves as the Chief of the Robotics Operations Branch at Johnson Space Center. From 2002 to 2017, Dr. Lucier worked at NASA's Johnson Space Center as a robotics flight controller and member of NASA's Robotics Operations Branch. In this role, Dr. Lucier led teams responsible for planning and executing the Space Shuttle and International Space Station missions involving the Canadarm and Dexter robots. From 2017 to 19, she served as lead of the flight control team responsible for operating the various information technology assets on board the International Space Station and NASA's next generation spaceships. Dr. Kimberly Hammakin currently serves as the Chief of the Robotic Systems Technology Branch at NASA Johnson Space Center, where she oversees the development of advanced robotic technologies for space exploration missions. Prior to this, she was the Principal Technologist for Robotics in NASA's Space Technology Mission Directorates, serving as the STMD Technical Expert. An advocate for robotics across all NASA centers for STMD programs. During her career as a robotics engineer at JSC, Dr. Hammakin developed human-robot interaction techniques and tools for the Robonaut and Centaur robots, the Space Exploration Vehicle SEV, and bipedal humanoid Valkyrie, among many others. In 2016, Dr. Hammakin was named one of the 25 women in robotics to know by RoboHub. Maria Bulat is the group lead for Intelligent Robotics Group at NASA Ames Research Center in California. She joined NASA Ames Research Center in 1987, working in the robotics field since 1995. Ms. Boulats has managed projects for NASA's Science Mission Directorate, Exploration Systems Mission Directorate, Office of the Chief Technologist, and Space Technology Mission Directorate, including ARC rover testbed, MIDP instrument integrations and demonstrations on the K9 and K10 planetary rovers, Human Robot Site Survey, Surface, Telerobotics, and AstroB. Ms. Boulats received her Bachelor of Science degree in Electrical Engineering from Stanford University and her Master of Science degree in Electrical Engineering, emphasis controls from Santa Clara University. What an amazing panel. And now they'll each provide a little bit more information about their backgrounds and the scope of their work and the context of their presentations. Prior to this program, we asked the public to submit questions and we had a very robust response. So we'll try to answer as many as possible during the course of our program. So first, I'd like to introduce Dr. Laura Lucier, who will provide our first presentation. Dr. Lucier.
Thank you very much, William. And I'd like to start by showing you guys a picture of the International Space Station. All right, so I lead the team responsible for performing robotics operations using the Mobile Servicing System, or MSS suite of robots on board the International Space Station. These robots were provided by the Canadian Space Agency, and I'll kick things off by telling you a little bit about the robots, what we use them for, how we control them, and how we plan our robotics operations. So here's a photo of the space station, and one thing you need to know about the space station is that it is absolutely huge. It's approximately the size of an American football field in length and width, and it has a habitable volume of a 3-bedroom home. It's made up of various modules, solar arrays, thermal radiators, and truss segments, all of which had to be assembled on orbit. And we could not have done that without using robots. Most of the American, European, Canadian, and Japanese parts of the space station arrived in the space shuttle's payload bay. After the space shuttle docked to the station, we used the space shuttle robotic arm called the Shuttle Remote Manipulator System, or Canadarm, to remove whatever parts of the space station were being delivered on that mission and hand those parts off to the space station arm, which we call Canadarm2, or the Space Station Remote Manipulator System. We then used the Canadarm2 to maneuver the elements into place, and spacewalking astronauts would usually bolt them together and perform various power, data, and thermal connections. In this drawing, you can see the Canadarm handing the P-34 truss off to the Canadarm2. This operation took place in 2006 as part of the STS-115 shuttle mission pretty early on in the space station assembly sequence. And here's a more detailed view of the SSRMS, or Canadarm2. The main robot arm is approximately 17 meters, or 58 feet long. We refer to the end of the arm that's out in free space as the wrist. The wrist is comprised of 3 joints, which allow roll, yaw, and pitch motion. The base, or shoulder end of the arm, also has pitch, yaw, and roll joints, and the elbow of the arm is comprised of a pitch joint. Because the arm has 7 joints, we have a lot of flexibility in how it can be positioned and the types of motion it can perform. At each end of the arm, there's also an end effector, capable of grappling whatever payloads we need to carry, and also capable of serving as the base of the arm. The arm symmetry allows us to walk it end over end between various base locations around the space station. We can also base the arm on a rail car, which is what's shown in this picture. We have 4 base locations on a robot called the Mobile Base System, which itself is mounted on a robot called the Mobile Transporter. So what you're actually seeing is 3 robots in this picture. The Mobile Transporter can be translated along rails on the space station's truss structure and parked at various work sites. So this, combined with those base locations on various pressurized modules, allows us to reach the majority of the American, Japanese, and European portions of the space station using the Canadarm2. When we perform spacewalks or extravehicular activity, we often take advantage of this to use the Canadarm2 to maneuver astronauts between work sites. This allows the astronauts to reach equipment they may not normally otherwise be able to, and it also provides them with greater body position flexibility for tasks like driving bolts or connecting power and fluid lines. Another advantage of using the robot to maneuver spacewalking astronauts is that it allows the spacewalker to carry or move large pieces of equipment, as you can see in this picture here. We also use the Canadarm2 to pre-position or hold large items for the crew during their spacewalks. In addition to constructing the space station and supporting spacewalks, we use the Canadarm2 to capture and release uncrewed cargo ships, such as the Japanese H-2 Transfer Vehicle, or HTV, as shown here. These cargo ships are called free flyers. They approach the space station slowly, and they hover approximately 30 feet away. We then reach out with the robot arm to grab a hold of them and then berth them to the space station. This particular operation really holds a near and dear place in my heart because I was the lead robotics officer for the HTV-1 mission in 2009, which was the very first time we had done this. We had past experience capturing free flyer satellites using the shuttle's Canadarm, but performing such an operation with the space station presented a lot of unique challenges. For starters, the cargo vehicle that you see here is very large. And I know it's hard to get a sense of scale from photos taken in space, but the HTV has a mass of about 16,000 kilograms, and it's also about 10 meters long, or roughly the size of a school bus. Now, one of our big concerns was related to the relative motion of the HTV vehicle compared to the space station. In the case of the space shuttle, if the satellite or the object you're trying to capture is moving, you can maneuver the space shuttle to match that motion. Or if the vehicle began to tumble or approach too quickly, you could maneuver the shuttle out of the way. But the space station is much too large and delicate for that. And so we worked for many years in advance of the first free flyer mission to think through and develop operational methods that would protect us from things like accidentally bumping or perturbing the vehicle with the robot arm, or perhaps a loss of space station or free flyer vehicle attitude control, or 1,000 other failures like a computer failure. One of the things I also really enjoyed about working on this project, in addition to having to solve those very technical challenges, was that the team working the mission included experts from Canada, the United States, and Japan, and I found it really interesting to find ways to work together to find solutions. In addition to capturing and releasing the Japanese H-2 transfer vehicle, we also used Canadarm2 to capture and release SpaceX's Dragon cargo vehicle, and Northrop Grumman's Cygnus cargo vehicle. Now, most of the robotics operations I've spoken about so far are controlled by astronauts on board the space station. And here's a recent photo of Jessica Meir at the controls of the Canadarm2. The crew used two hand controllers or joysticks to control the robot for things like capturing free-flying vehicles or positioning spacewalking astronauts close to the station. Using hand controllers allows for ad hoc changes in the robot's position as well as a quick response. One joystick controls the robot's translation or motion along the X, Y, and Z axes, and the other controls the robot's pitch, yaw, and roll motion. We use a variety of command and display reference frames to control the robot's motion and to define the end effector's position in space. The crew is also able to tell the robot where to go by specifying the spatial coordinates that they want the end effector to move to, or by specifying the position of each of the robot's 7 joints. These types of motions are commanded through a laptop computer instead of using the hand controllers. Now, whenever the robot is moving, the crew monitors its motion using views from cameras mounted around the space station, as well as on the robots themselves. These views are displayed on monitors, along with other data or telemetry from the system. It takes us about 130 hours to train an astronaut to operate the Canadarm2. A lot of this time is spent learning how to interpret those camera views to ensure that you don't hit anything with the robot, and also learning how to apply nice, smooth hand controller inputs to ensure that the robot's responding motion isn't jerky or dynamic. Even though the crew are trained before their mission, we sometimes don't know exactly what robotics tasks they'll be asked to perform before they launch. And things like the hand-eye coordination required for smooth hand controller inputs are skills that degrade over time. So before performing each robotics operation, the crew practices it on board the space station using a robotics simulator. In addition to the Canadarm2, mobile base system, and mobile transporter robots, my team and I are also responsible for operating the Dexter Robot, or Special Purpose Dexterous Manipulator, which you can see in this photo. Dexter's a 2-armed robot, and we use it for performing more delicate tasks. Each of Dexter's arms is approximately 3.5 meters or 11 feet long, and the robot has 7, and each of the arms has 7 joints, just like the Canadarm2. Dexter also has a body roll joint and a platform for stowing payloads. We typically use Dexter to load and unload those cargo ships, and also to replace equipment that has failed on the space station. Like the Canadarm2, Dexter can be based at various locations around the space station, but most often we pick the robot up and move it to required work sites using Canadarm2, like you can see in this picture. This allows us to reach a variety of equipment around the space station. As I mentioned, we use Dexter to perform delicate operations, such as the replacement of cameras on the mobile base system and Canadarm2, as shown in this animated sequence. As you can see, we perform a combination of Canadarm2 and Dexter maneuvers to complete the operation. In this animation, you can see Dexter being used to swap out a failed thermal system pump with a replacement. Often, these types of operations have to be done with a very quick turnaround because this equipment is critical, keeping the space station operating safely and nominally. One of the really cool things about the Dexter robot is that it has force moment accommodation, or a sense of touch, which allows it to handle delicate equipment without fear of applying enough force to damage the equipment, the surrounding space station structure, or the robot. Force moment accommodation also allows us to use the robot to perform tasks that require a high degree of accuracy, such as sliding delicate payloads into and out of very tight spaces. In addition to using Dexter to move cargo and science payloads around and to repair the space station, we also use the robot to perform experiments and develop and test new robotic technologies. One really cool example of this is the Robotics Refueling mission payload, which was developed by a team at the Goddard Space Flight Center. This experiment investigates tools and methods for repairing and refueling satellites in space robotically. Some of the things we've tested as part of this project include using special tools with Dexter to cut through multi-layer insulation blankets, which is what we're preparing to do in this picture, and also connect and disconnect electrical and fluid jumpers, and to control articulated cameras. Now, originally, the operations concept for the mobile servicing system robots was that they would be operated exclusively by astronauts on board the space station. But as the demand for the crew's time increased and the systems became more complex, we realized that we could decrease the crew's training time, free them up to perform other tasks, and perform a greater amount of robotics operations overall if we instead controlled the robots from the ground. And so a majority of the command and control of the robots I've been talking about today, with the exception of spacewalk support and free flyer vehicle capture, is performed from the ground by robotics flight controllers, which is a job I was honored to do for about 15 years before I moved into a more managerial position with the team. Our flight control team has about 50 people on it, and we all have engineering, math, or science degrees. We work from NASA's Mission Control Center in Houston, and also from the Canadian Space Agency's Control Center near Montreal. Our flight controller call sign is Robo, and we trained for many years to become experts in the electrical, mechanical, video, software, and thermal systems that make up the robots. Flight controller training consists of classroom sessions, a lot of homework and studying, and many hours spent in simulations where we learn how to respond to every imaginable failure and emergency. We have 3 levels of robotics flight control certification. The first level and corresponding mission control console position is called MSS Task. The task officer is responsible for making sure the ground team or the onboard crew are commanding the robot along the expected trajectories. They are also responsible for making sure the cameras are positioned to view the robot motion and that the operations are proceeding on schedule. The second level of certification is as an MSS Systems Officer. This person is responsible for understanding all of the technical workings of the system and monitoring the health of the robot during operations. They have to watch and make sense of literally hundreds of pieces of telemetry or information while the robot is operating. And they're the one responsible for figuring out how to troubleshoot or work around system failures when they happen. The third and highest level of certification is as a front room controller, or Robo. This person leads the robotics flight control team, coordinates with flight controllers responsible for the various other space station systems the robot is interacting with, and makes recommendations to the flight director. When we perform robotics operations, we also have teams of engineering experts in Houston and Canada who monitor the system and provide us with advice. So when you look at a picture of the folks working in mission control, like the one you see in front of you, I find it interesting to know that the actual number of people supporting whatever task or operation is being performed is actually much, much larger than the few people you're seeing in the main flight control room. Now, a big part of being a flight controller is understanding that our performance could make the difference between life or death, or between mission success and failure. So in response, we spend a lot of time preparing for each and every operation we perform. Regardless of whether the robotics operation will be performed by an astronaut on board the space station or a flight controller on the ground, we spend days or weeks planning every aspect of the operation in advance. So planning typically begins by determining what trajectories or paths we need the robot to follow. And that's not as easy as it sounds. If you consider the example on the screen, where we want to move the Canadarm2 from the dark blue initial configuration to the dark green final configuration. So these positions appear to be pretty close to each other, but various limitations of robotic kinematics and of the space station workspace mean that for this example, we actually have to move the robot through 4 intermediate configurations represented by the other blue, cyan, and green robot models shown in the picture. We also need to consider rules against getting too close to the space station and things like payload thermal considerations. Oh, and we also have to avoid things like radiation fields emanating from antennas that could cause damage to the robot, or if we entered them, could result in erroneous data measurements or interruption of data. In this picture, the large purple area represents a laser field, which could damage the arm. And as you probably saw in the animations I showed earlier, the resulting robotics trajectories appear to be a choreographed ballet and a great combination of maneuvers. Once we've determined the paths the robots will follow, we write step-by-step instructions for the flight controller or astronaut to follow when executing the operation. And we do this because we really don't want to leave anything to chance. We spend a lot of time brainstorming anything and everything that could go wrong, and we also develop instructions for recovering from those scenarios. And I'm going to wrap it up there. I think I've provided you with a bit of an overview of the mobile servicing system robots on the space station and how we operate them. Thank you.
Thank you, Laura. That was absolutely fascinating. I also really enjoyed the animations. It really helped illustrate the role of robots in supporting space exploration. And it was fascinating to learn about your background and the role of mission control in supporting robotic missions. Our next speaker is Maria Bulat. Maria.
Thank you. Hi, I started working in robotics about 25 years ago when I saw that the robotics group in my division seemed to be having the most fun, so I decided to join them. Since then, I've been working on a variety of projects, including research into planetary rovers and free flyers. Some of the earlier robots I worked on were similar to the Mars exploration rovers, Spirit and Opportunity, which interact with humans in a very remote way. The nearest human is millions of miles away and only talks to them a few times a day. So we looked at how to make the robots as smart as possible so that the human operator could send very high-level commands and trust that the robot would keep itself safe and successfully execute the commands. Later, I worked on robots that are meant to team up with humans a little more closely to explore Mars or the Moon. We considered how robots can help humans explore by first doing some prep work before human crew arrives, for example, scouting or setting up infrastructure. Then we looked at ways that a robot could interact as an assistant once crew arrives, for example, carrying tools or instruments or samples. And finally, we studied how robots could continue to explore after the human crew leaves, for example, taking follow-up science measurements. My more recent work has been concentrated on robots to work with astronauts, either controlled by them from space or to work alongside them in the same vehicle. Smart Spheres was a proof of concept of a free-flying robot inside a vehicle, for example, the ISS or the Lunar Gateway, that could take over some of the chores that astronauts currently do. For instance, crew often needs to do sensor surveys to check on vehicle health, air quality, or sound levels. So we launched a smartphone and attached it to the Sphere's satellites on ISS and gave it a little more computing power and some sensors like a camera. We showed how a little free-flying robot could perform surveys while under control from the ground, thus freeing up crew time. So what we're watching here is the Spheres, that sort of red ball-shaped robot, and on the front of it is a smartphone. And it's flying a sort of lawnmower pattern, taking images of the panels that are on the wall. And this allows us to do a visual inspection of those panels. So now we see the control station on the ground, and you're seeing the live video in that center section of the control station. So we see exactly what the robot's seeing. And then on the right, we see a virtual world showing that the pattern that the robot is flying, that sort of, you can see the lawnmower pattern there, and what the camera is imaging. So the sort of blue cone shape that you see is showing where the camera is pointed. We also, on the left-hand side, show the plan that the robot is executing, the different steps of its current plan. Next, I worked on an ISS experiment called Surface Telerobotics. On this project, we had an astronaut on the ISS controlling our planetary rover test bed in our rover testing ground at Ames Research Center. We refer to ourselves as the upside-down payload because most payloads on the ISS are hardware and they're controlled by ground controllers. However, we had our hardware, the robot, on the ground on Earth, and it was controlled by the astronauts on ISS. And we were studying how crew in orbit around Mars or the Moon can control a robotic asset on the surface. The communication delay to orbit is shorter than back to Earth, so it's easier for an orbiting crew to handle fast-paced operations. We studied how to give astronauts good situation awareness while they're acting as robot supervisors so that they can deal with any contingencies that come up. So what we see here on to the left is the K-10 rover in our roverscape at Ames in California. On the right is Chris Cassidy controlling the robot. Chris is actually back on station right now and is the commander of the current expedition. And then in the center there, you see our control panel. So you can see the heritage from the Smart Spheres, very similar look and feel to it. Although in this case, we didn't really have live videos, so we're looking at all virtual an all virtual display there. My most recent robot is Astroby. Astroby is a free-flying robot for the ISS, and it has a lot of heritage from these past projects. Astroby is meant to be supervised by ground controllers, but can also be controlled by crew on the ISS. So in this image, we see in the lower left is the two of our Astroby robots. We see Bumble on the left and Honey on the right. Honey's actually docked upside down. That's the correct way to be docked. And we have a third robot called Queen that's in stowage and hasn't quite woken up yet on ISS. The high-level goals for our Astroby human interaction was to make Astroby very easy to operate and to require minimal training from ground operators and crew. We also wanted to enable future human-robot interaction research, so we provided some basic infrastructure that lets future guest scientists experiment with how a robot can communicate with crew. And finally, we wanted to be a good crewmate for astronauts. So we thought really hard about how crew, who very often only have one hand free, could physically interact with the robot. For example, where can they hold on to it? How can they easily switch batteries or payloads, etc. And again, for the ground controllers, there in the upper right, you see our control station. Again, looks very familiar to those past projects. And we see the virtual world there in the lower right-hand corner of the control panel. But we also can stream video to the control station from Astroby. There are just different tabs that the user can bring up to watch that. So when we designed the Astroby control station, we envisioned 3 levels of users. First was crew, where we wanted really minimal training. So just 20 minutes of onboard training enables crew to control the robot. They can run plans that are developed by guest scientists on the ground and then deal with contingencies on the robot using teleoperation. We decided not to include the capability to build plans for crew, and we may actually regret that because astronauts like to run their own experiments on weekends, and they may come up with wanting to develop their own plans. The middle layer is operators. So for example, flight controllers in Houston or payload controllers in Huntsville. And these are non-expert users, but they know enough about the robot that with about 2 hours of training, they can actually create plans using a planning tool. So it's basically the crew interface with the addition of a planning tool. And then finally, you have the engineering layer, which this is now for expert users. These are Astroby developers and facility engineers or guest scientists who have really familiarized themselves with large portions of the system. Additional tabs give them more access to deeper controls and telemetry. So these are some of the interfaces that we've provided for human-robot interaction. What you see on the left is the animation of the eyes on Astroby, and that just conveys to crew that the robot's awake. It can also be used to give some indication of, so for instance here, the flashing eyes can say back up or give an idea of which way the robot's going to be turning. We also provided some additional indicators that tell the crew whether the cameras are on, whether there's a microphone on, and what's basically happening on the robot. We have signal lights that can be used to indicate directions or, as I said, future ideas that other human-robot interaction researchers can try out. We have a touch screen. We have a flashlight so it can light things up for the crew. And we have a laser pointer too, so that the robot can point at things. If they want to indicate something to crew, they can actually point at it using the laser pointer. And finally, we have the speaker and microphone so that the robot could use voice control, although that's not a current capability on the robot. So the next slide is actually a fairly long video. Hopefully we'll get through most of it here. This is of Astroby's first autonomous survey. So this was several months ago. We were flying Bumble. So Bumble is blue. You see the skin on Bumble there. And it can autonomously undock and fly and do its mission and then return to its docking station and recharge. There's a few jerks in this just because I cut out the pauses. So Astroby did stop from time to time to think. And so for the purpose of cutting down the length of the video, those little pauses are cut out. So that's when you see a bit of a jerk. That's what's going on. This is about 2 times the speed that Astrobee flies, just to make it a little quicker as well. And what we see here is Astrobee is surveying a panel on the wall in space station. So this is very similar to what we saw in that Smart Spheres video, but with a much more capable robot. You can see it flies very smoothly. And we're not quite doing a lawnmower pattern here. We're doing basically a square looking around the edges of that, that panel. So astronaut Christina Cook was our observer for this. So again, the idea with Astrobee is to try and take up some of those chores that crew currently has to do to maintain a vehicle, and part of that is inspections, and so that's what we're showing Astrobee taking care of here. So the next part of this video is actually just a little bit of testing that we did of the flight of Astrobee, just verifying that its localization, you know, if it understands where it is correctly. And so we flew back and forth a couple of times around the module. We're inside the Japanese experiment module here. We have a little bit more dramatic flying in this part because this was a test. So we'll have some big angles. The way Astrobee navigates is it has an onboard map of features inside the space station. So what it does is it looks at current images that it sees and compares it to the map and triangulates its position. So it's just using cameras. It doesn't need any kind of beacons or markers in order to navigate. And the idea there was that we wanted to minimize the additional infrastructure needed inside the vehicle. So we're basically using natural features of the environment. You can see we tend to turn fairly slowly because rotating can cause a lot of motion blur in the imagery, and so that's why rotations seem slower than translations. And this is all autonomous, so right now nobody is sending commands to the robot. We basically sent it a plan with a bunch of waypoints for it to travel to, and then said go. So we can actually let Astrobee continue to operate when we have loss of signal, and then when we get signal back on the ground, we can see how far Astrobee got. If it does encounter a problem or sees an anomaly, it will stop what it's doing and just station keep, stay where it is, and wait for an operator on the ground to come back and tell it what to do next. And here's our dock. Moving back up to our docking station so that we can recharge. Almost there. And success. And that's everything I had for you today.
Great, Maria, thank you. That was absolutely fascinating. I have a lot of questions and I'm looking forward to the Q&A section. And I'm sure that our viewers do as well. Our next speaker and final speaker is Kim Hammakin. So Kim, you are up next.
Thank you, William. So I'd like to start off with this picture. This is one of my favorite pictures ever. This is me sitting in a large building at Johnson Space Center, surrounded by almost all of the robotic systems that have been built by the group that I now manage at Johnson Space Center. And you can see there's a variety of different robots. So when I was asked if I would like to speak at this series, I kind of had trouble deciding which robotic system I wanted to focus on. But for all of these robotic systems, I actually have been doing a kind of form of human-robot interaction. Really, a remote human robot interaction, because many of these systems we think will be operating without crew or during periods where there are no astronauts around. So someone on the ground has to actually make sure that they don't do things wrong and that they're doing the tasks that they need to do. But today I've decided to really focus on one of the specific groups of robots. So today we're going to talk about Robonaut. Robonaut is a project that began over 20 years ago at Johnson Space Center. And the idea was that we could design a robot that could fit into a human system, use the tools that were designed for the people, use the work sites that were designed for the astronauts, and actually kind of give the astronauts another crew member who doesn't have to eat, who doesn't have to breathe, so that they could do some of the more difficult and interesting external vehicular activity tasks, whereas we could have a robot that's actually doing kind of the boring, monotonous things like wiping down handrails or replacing broken handrails, the sorts of things that astronauts like to call their Saturday afternoon chores. So we have been working with Robonaut over these years, and in 2007, we actually had General Motors come to us and say they wanted to partner with us on a robotic system like Robonaut. So we actually started developing Robonaut 2, which you see standing next to the astronaut, in 2007. General Motors was very interested in having robots that could stand right next to people on their manufacturing lines. And we wanted to kind of take the technology further with Robonaut, seeing as how the original project was started around 1997. So technology had definitely increased by that point. And we really wanted to focus on something that could work around the astronauts. So we developed this robot together. It was what we call a prototype. And the idea was that it would allow us to understand some of the technology challenges so that we could eventually make a better Robonaut assistant, astronaut assistant robot. And lo and behold, we were asked by the International Space Station if we could make one of our Robonauts flight worthy and put it up on the space station to do some testing with it. So we had to very quickly change out electronics inside of the robot, and some of the sensors that are on the robot had to be changed so that it would survive a launch up to the space station, that it would survive the type of radiation that it might see in the space station, and also that it wouldn't start off-gassing and causing some detrimental effects to the astronauts on space station. So we actually launched on STS-133 in February 2011. And the original Robonaut that launched was only a kind of half humanoid. And you can see that it's just basically sitting on a post. But this is really the first testing that we did with Robonaut on space station. We wanted to make sure that it could actually push buttons and flip switches and do the sorts of things that we were expecting a Robonaut type robot would need to do inside of a human space environment. And because we were so focused on getting the hardware itself able to withstand launch and function on the space station, the software side that actually controls the robot and lets it, move its arms and see things was not as advanced as we would like to have gotten. So in these initial checkouts and tests that we did with the robot on space station, this was really more of an automated system. We had ground controllers who were actually initiating some of these programs, but the robot isn't necessarily searching for the blue button. It knows where the blue button should be and it punches it. If it does something, if it doesn't punch the button, then the human operator actually has to step in and fix the robot so that it will punch the button in the correct place. So this isn't really what everyone thought we'd be seeing with robots walking around on their own and doing their own things. But it was a first step, and it was a great test to just make sure that this robot could actually function in a space station environment for future space exploration missions. So another type of system that we use to control this robot remotely is something called Telepresence. And we used this quite a bit with Robonaut 1 back in the day. And now it's much easier to do because you're essentially using a virtual reality helmet and some sensory gloves that understand what kinds of motions you're doing with your hands. And you're pretty much an avatar in the robot. So you step into some gear and the robot will do everything that you do. We'll actually see some of the tests we did with a human, or with the astronaut operator in the VR suit, which you can kind of see in the background, operating Robonaut on space station and kind of playing with some tape with one of the other crew members. However, it turns out that the astronauts on the space station are very busy. So we really want to be able to have ground controllers operating these robots, supervising these robots, instead of relying on another crew member on the space station operating the robot that's on the space station. Like Laura told you earlier, you know, it saves quite a bit of crew time if we can have people back on Earth operating these robots. So if we start the next video, you'll see Robonaut doing some what we call autonomous activity. And the robot you're seeing in this is actually Robonaut with its 2 legs. So we did develop what we call climbing legs for the robot to actually be able to climb around on the space station. And you'll see the blue handrails in this are the same handrails that are on the inside of space station. But what we're doing here is we actually have a lot more autonomy built into this robot. But you do see the people. We're always needing people to do some of the interaction with the robot to make sure that it can do its tasks properly and that it's not accidentally grabbing a blue, you know, something else blue and long and skinny on the space station that looks just like a handrail. So Robonaut actually had some problems up on space station once we put the legs on it in the space station. And so we actually had to bring that back down. We found the problem. It's all packed up and ready to go. But while we aren't able to do testing on the space station, we actually put the robot in something, our active response gravity offload system, which itself is a robot, that offloads the gravity on the robot. So it seems like it's working in 0G. So the video you're seeing right now is in that test area. But you can see all of those little markers, those funny looking markers, those are actually allowing the robot to visually align itself with the objects that it needs to interact with, so that we don't need the people on the ground to tell it precisely where an object is that it needs to interact with. They're actually just saying, okay, you need to go do your task, this specific task, and the robot can do it itself. So that we're kind of decreasing the amount of direct interaction that we need to have with the robot, but still keeping the people in the loop, making the higher level decisions. So right now we're just kind of waiting for Robonaut to get back up to the space station. We're only able to go on the Northrop Grumman mission cargo vehicles. So we are patiently waiting for our next slot, which right now we're hoping will be sometime next year, so that we can do some of the testing that you saw in that video up on the space station. And at the same time, we're also working with the Ames Research Center, Maria's group specifically, on a collaborative project that we're hoping we will be able to test on the space station with both Astrobee and Robonaut involved, and having these 2 robots do some collaborative activities. We're focused on some of these tasks because we think that when the Gateway vehicle, which is NASA's future space exploration mission, it will be a small space station-like vehicle orbiting the moon, and we won't have astronauts on that 24/7, 365. So we think that we'll probably need some robotic systems to manage those habitats and maintain things in them. So we're actively looking at how we can use the space station and the robotic systems we're developing to get ahead of the problem areas we think we're going to have with these robotic systems. So that's about all I've got for now, and just one of the robots that I have had a lot of human robot interaction with. but happy to take questions about all of the others.
Great, Kim. Thank you very much. All three presentations are absolutely fascinating. I have so many questions for all of you. Absolutely, it's so interesting. One question actually to put out to all of you is this whole question about giving the robots human characteristics. And why do that? For one, why give them certain interpretation of emotion or human characteristics? I understand from one, so they fit within the same structure that humans use and can use some of the same tools and other things, but there are some others that may convey, or some people may say communicate, some level of either emotion or response. Is there a kind of a theory behind this or practice behind adding kind of anthropomorphic characteristics to a robot?
So I will say the form of a humanoid for Robonaut really was specifically for being in human environments and being able to be teleoperated when humans in a telepresence suit. So I wouldn't say that it was developed because it would make it more friendly looking or anything. Actually, I think that the work that Maria and her team are doing with Astrobee and the lights and sounds that they're hoping to convey to the astronauts is the more interesting area, because they've done quite a bit of work and research in why that would be useful.
Right, for us, we're a free-flying robot. We can go pretty much anywhere in the space station, and just part of the safety story is, showing the intent of the robot. So if crew knows robot's moving in a certain direction, they know not to go that way, so they don't clash, they don't interact with it unintentionally. But also for Astrobee, we wanted to give them personality, and part of it is because we are going to be flying around mostly autonomously around the space station and interacting with crew. We just want to be friendly neighbors, friendly crewmates to the astronauts. And so giving the robots a little bit of personality and individuality also, so you recognize, one robot can distinguish one robot from another, was very important. So that's why we gave them the eyes and the colors and the names, is to make them more friendly.
So specific to Astrobee, Maria, I'm curious, what propels Astrobee? How does Astrobee actually move? Because it seemed very agile, and we know you're in a microgravity environment where typically astronauts have to physically grab something to propel themselves. So what is the actual propulsion technology that enables Astrobee to move around?
So Astrobee, so the old system, Spheres, used a cold gas. So it had cold gas canisters, CO2 canisters, like in paintball guns, and then nozzles that allowed it to move around. Astrobee is fan-based, so it will not work in a vacuum, so it can't go outside space station. It needs the cabin air in order to move, and there are two impellers, one on either side in the propulsion modules. They counter-rotate so that we cancel the gyroscopic effect, and that lightly pressurizes the plenum of the propulsion module. And then there are 6 nozzles, so the 12 total, so 6 per propulsion module, 12 total, 2 on each face of the robot. And then just by opening and closing those nozzles, we get thrusts. So we have limitless propellant because we're just using cabin air. So really, we just use our consumable is battery charge. So we have a docking station. We can go dock in, charge up, and then go back out again. So, and that was primarily, it was again looking at freeing up crew time. For Spheres, crew had to change out those CO2 canisters. And so by being an all-electric system that can recharge itself, there's really no setup time to use Astrobee, and actually Astrobee can work without crew at all.
Fascinating. Well, this is a question for all three of you, and maybe we could begin with Laura on this. How do we ensure the safety of the crew and the astronauts? Are there features built in so that if you are either physically maneuvering a robot, doing an activity, and an astronaut is participating and interacting, how do you ensure the astronaut is not injured in some way?
It's a really good question, William. Our robot in particular is very big and very strong, and we're always very much aware of where the robot is relative to the pressurized modules of the space station. And then, of course, as you mentioned, when we're doing a spacewalk, we're extra vigilant about working in the area of the spacewalking crew. We have all sorts of safeguards that we put in place. For example, when we are operating in close proximity to the space station, so within about 5 feet of clearance, we put constraints on the current, the amount of motor current going out, as well as the speed at which the robot can move, so that if we were to have a surge or accidentally input the wrong direction of motion, that motion would be much slower and start and stop with much less power than it would when we're operating further away from the space station, for example. We also have requirements to have visual views of the robot in the spacewalking astronauts to the greatest extent possible. And we have very strict communication standards that we use. So when the robot is maneuvering a spacewalking astronaut, the astronaut inside the space station and the astronaut on the end of the robot arm or in the vicinity of the robot have definitely rehearsed in advance and then have very clear and expected communication calls that they're going to make when asking for motion or asking for that motion to stop.
Fascinating. Maria and Kim, do you have other things to add to the comment about astronaut safety with the technology that you're working with?
Yes, so for Astrobe, we put bumpers on the corners and a little bit of padding over the propulsion modules. We're a little bit lighter weight, and because we are free flying, there's not going to be a lot of force exerted against an astronaut. We also limit how fast we fly. Although the funny thing is, for crew safety, the biggest issue is not how fast we fly, it's how fast the astronauts move, because we can't move nearly as fast as the astronauts do. So the danger is more that a crew member will come zipping in through a hatchway and bump, run into Astrobe. So what we do is we put up signals, so like flashlights, or we've considered like making beeping noises whenever we go through a hatchway, just to warn crew to slow down when they're coming through a hatchway.
Interesting. Kim, how about for Robonaut?
So this was a very interesting experience for us, because we had to ensure the safety of the crew inside with this hulk of a robot that would be operating right next to them. And one of the things that we did with the design of Robonaut 2, and that we're doing with all of our manipulator robotics, is actually having what we call series elastic actuation. And what that means is that we put a spring into the motors that drive the joints so that the joints can be flexible, and we can actually program them to be very flexible and compliant, or we can make them really stiff and strong. And so that was something that actually enhanced our safety story when we went to put Robonaut 2 on space station. Number one, though, there's always a big red button. So you hit the big red button and the power shuts off and the robot can't do anything. So for space station, it's pretty easy because there's always a second person who wouldn't be interacting with the robot, who could just hold the button. And additionally, when we hit the button, we allow the robot to just free float. We have brakes in all of our joints on Robonaut 2, but we decided that we don't use those on space station, because then the robot could get into a position where it's kind of cornered a crew member or put a crew member in danger. And, we have quite a few backups. We have redundant systems on the robot to make sure that it won't fail in a way that is dangerous. But those are some of the different things that we did to get Robonaut 2 safely onto space station.
Well, what's so fascinating about the work all of you are doing is it is research and development. You're constantly learning and developing new iterations, new refinations, way to help advance space exploration. And Kim, you spoke a little bit about plans for Artemis and Gateway, which we know are the priorities of NASA. So I'm curious, what do you see coming down the road in the near future? What are some of the priorities or applications that you all are foreseeing for the role of robots to support the Artemis program and Gateway, and ultimately our having some kind of colony on the south pole of the moon?
Well, I'd like to pipe up about a robot that our branch is actually developing called the Viper Rover, which is going to go scout for water and other resources at the South Pole before humans actually land there. And we had a big announcement today that the company Robotic, which is one of our lander providers, will be delivering the Viper Rover to the moon in the end of 2023. So that's an area where we need robots to go do something before crew gets there. And we're hoping to continue with commercial partners in the future to continue to do these sorts of things. Viper will simply just be mapping out the surface, but there's all sorts of tools that can be used to process any water that's found, to build up habitats for the humans on some smaller rovers like the Viper Rover.
Fascinating.
William, you mentioned some of the research and development that we're doing. And, I mentioned earlier the Robotics Refueling mission, where we were experimenting with different tools to perform a much wider array of operations using the robots. But when we look forward to Artemis and some of these, my team is looking at a lot of the same tie-ins that Kim and Maria's teams are looking at, and that's related to increased autonomy of the robots. When we start talking about deep space exploration, or even Gateway, where we only have the crew present on the space station for relatively short periods of time, we need the robots to be able to continue on with the science or the vehicle maintenance and these types of things. And so we're spending a lot of time on the space station investigating things and improving things like machine vision systems and autonomous task development and execution, so that we can greatly reduce the amount of human interaction or even oversight that goes into performing these robotics operations.
Fascinating. Maria, do you have some thoughts?
I was just going to pipe up also with Kim. Kim mentioned earlier about robots maintaining the gateway. And so her group and my group are working together actually on a system that the vehicle systems and robots on board can work together to deal with anomalies and maintenance and possibly even cargo handling on the gateway.
So it sounds like Roomba has a future on Gateway. I know that, and I'm making a bit of a joke there about this, but I know maintenance is a big issue on station, the cleaning that astronauts have to do. So are there technologies being developed that take care of some of that kind of fundamental but really important maintenance, especially as we send humans to live long-term in these habitats? What are we learning from station and how robots can support that?
One of the things that we're learning on the ISS externally, because of course my robots are outside, so that's my area of expertise, is we've greatly increased the amount of tasks that we can do from a space station maintenance or repair standpoint. So originally, for example, there were some computer units that if one of these computer units failed, we anticipated that we had to send some spacewalking astronauts outside to go and swap out those computer units. And of course, performing a spacewalk is incredibly risky, takes a lot of time, and so we want to avoid doing that if at all possible. And so now we've made those what we call orbital replaceable units, ORUs, or those components, a little more robotics friendly. And I think that's a big part of our world and our community, is trying to design systems that are robotics compatible in the first place to enable this. So for example, there was some equipment on the outside of the space station that was covered in protective thermal blankets that prevented the robot from being able to access the bolts or grab onto those pieces. And we've since, on other spacewalks, taken advantage of the opportunity to remove those blankets, so that if those components fail in the future, we can easily access them with the robots and save ourselves having to send the crew outside. So, I think having a holistic viewpoint about what robots can do, but also what their limitations are, is going to be a big part of what enables this in the future.
Fantastic. Well, I am so intrigued by your level of knowledge and experience. How, we have a lot of young people who participate at Space Center Houston and our programming, and if they're interested in a career in robotics or becoming involved at NASA Johnson Space Center in this area of research, or any of the NASA centers in general, What are your thoughts on kind of possible career paths? What can people do to learn more and actually pursue robotics as a potential career in the future?
Well, one nice thing about robotics, it's a very dimensional problem, right? So it requires all sorts of skills, from electrical engineering, mechanical engineering, to human-robot interaction. So, psychologists work in robotics. So you can really, do what you love and still find a place in robotics.
Yes, I second that. It is, the best thing about robotics is that you will have a team around you to support you, because you cannot develop robotic systems in a vacuum. But there's all sorts of engineering degrees, like Maria said. There is a lot of software development for robotics, and understanding how to develop code for solving some of the robotics problems will help if you're interested in kind of a software development future. And like Maria said, cognitive sciences, psychology, human factors, all of those areas still come into play with robotics. So it's really broad. You just need to make sure that you take your math classes, take your science classes, but you don't necessarily have to be an engineer to become a roboticist.
And for those interested, at a younger age, there are all sorts of great robotics clubs, Boy Scouts, Girl Scouts. A lot of these programs encourage and have teams or clubs that are developing robotics, a lot of schools as well. The first robotics competition comes to mind. So I would encourage folks to go out there and do a little web browsing and see what's going on around you, or perhaps already exists at your school or in an organization that you're already associated with.
And then once you get to be maybe a junior or senior in high school, you can start looking at internships. I think the minimum age is 16. But all through college and even graduate school, you can intern at NASA centers.
Wonderful. Thank you for those words of guidance. I'm going to put a little plug in for Space Center Houston as well, and I'd encourage people really beginning. We have classes beginning for 4-year-olds actually in computational thinking, and so you can participate in our summer programs as well as through our Innovation Gateway program, where we actually work with NASA and the commercial sector with community competitions, and some of them actually have cash prizes. And most of them are focused on robotics and robotics research. So it's a great way to tinker and be involved and explore and see if that could be a future path for you as well. I wanted to we're coming to the end of our time. I'm having such a great time talking with all of you, and I'm just absolutely intrigued with the work that you do to advance space exploration. And I'm wondering if I wanted to give you each a time for some closing thoughts about the work that you're doing and kind of the trends you see going into the future.
All right, well, how to sum it up? I feel really fortunate to get to do what I do. When I was a very little girl, I developed a passion for human space flight and human space exploration. And, at the time, I didn't know that it would end me in robotics. I was just looking for the opportunity to fulfill that passion. And in the end, I love robotics. One of the things I like best about my job is the immediate gratification that comes from typing a command into a keyboard and then looking up at a screen and seeing a giant arm way up there in space move its way across the sky. And I find that really rewarding and a lot of fun. And I love that my work is multidisciplinary and a little bit different every day. So, I'm happy to be here, and I'm excited about what the future is bringing. We've mentioned a lot of the cool stuff that we've all been doing. We're starting to explore the greater use of virtual reality, for example, in training the crew. So I'm really excited about what the future brings and really thrilled to be a part of it. Thank you.
Oh, thank you so much, Laura. Maria.
Yeah, I also at a young age was very interested in math and science fiction, and wasn't quite sure, career-wise. But then in the 7th grade, I read an article about women engineers at NASA. And so that got me really excited and interested and wondering what an engineer does. And so, I educated myself on that. And And then when I got recruited in college by NASA, it was my dream job, and so I've been in my dream job. It's been really great, and yeah, I agree with Laura that it's so exciting working in robotics and seeing this device doing what you told it to do in space. I also think it's a little bit like bringing up kids too, seeing them grow in capabilities and their abilities and being able to think more critically about the world around them. So, and yeah, I'm really excited for the future of robotics. Technologies are moving fast, computational technologies, and so we're seeing more and more capable robots in space, and we'll probably see them exploring the moon very shortly.
Great, thank you. Kim.
So I actually kind of tripped backwards into robotics as an undergrad. I was not expecting to be part of it. I didn't even know it was a thing. And I just happened to be doing some work in computer vision, and there was a robotics lab at my school. So for everyone out there, you don't have to plan for a future in robotics. It can sometimes just happen. And I also never thought I'd work at NASA. Thought that was a lofty goal, and here I am many, many years later. I've found that I've enjoyed robotics tremendously because there's always a problem to solve, and there's always something new coming down the line technology-wise that then makes what you're doing in robotics even more useful. And I think that what we're looking at for the future of NASA is much more robotic involvement for our human exploration missions. Right now, most of our robotic systems in space are off by themselves, doing things without humans. And I'd like to see quite a bit more of this human-robot interaction with astronauts someday. We have so many unique challenges in the field of robotics for NASA with time delays between when we send a command on the Earth to when it reaches a robot in space, to the environment that the robots are in. Surface of the moon is very harsh. That, those are the sorts of problems we are trying to figure out very quickly. But so we don't get to focus so much on things like, how do you have an astronaut trust a robot and work with a robot like it's a partner. But I'll be very excited when we do get to that point. We have a lot of interesting research going on in those fields at NASA, but we're so focused on getting things ready for Artemis that those research points are at kind of a lower technology level. So I'll be excited to see when we really have kind of true human-robot interaction with the astronauts and robots on a space mission.
Wow, thank you. I am totally intrigued by our conversation today. I want to thank our panelists for sharing their experiences, insight, their incredible innovations that they're working on. And I think we need to have you come back in about a year or so to kind of see how things have progressed with all of your respective research projects. So I want to thank our audience for joining us today for our Human-Robot Interaction Thought Leader Series brought to us by UTMB. And look forward to having you join us at our future Thought Leaders programs here at Space Center Houston. Thank you.